In this video, we're going to learn about trigonometric functions and their transformations. We will learn how to sketch and use the graphs of sine, cosine, and tangent functions. We will also understand and use the transformation of the graphs of y equals f of x, given by y equals f of x plus a, y equals f of x plus a, y equals a f of x, and y equals f a of x, and simple combinations of these for trigonometric functions. So this video is basically a part 2 to the transformations under the functions topic. So if you haven't watched that video, watch that one before you start this one. So it should pop up in the top right hand corner right about now. The sine function is typically denoted by y equals sine x. And in this case, you can see that we've drawn it from negative 2 pi to 2 pi. And if you're unfamiliar with radians, that's negative 360 degrees to 360 degrees. As you can tell, after 360 degrees, this function repeats again. So this is what we call a period. It has a period of 2 pi radians, which means that it completes one full cycle after 2 pi radians. And then we have our cosine function, which is denoted by y equals cos x. Again, we've drawn it from negative 2 pi to 2 pi, which is negative 360 degrees to 360 degrees. And you can also tell that it has a period of 2 pi radians, because after 2 pi radians, it repeats again. Finally, we have the tangent function, which is denoted by y equals tan x. Now this graph is a bit different because it has these little red lines that are dotted. We call those asymptotes. At these points, the graph of tan x is not defined. And if you check on your calculator, if you substitute these values, for example, y equals tan of negative half pi, you will get an error. So at these points where we have these red dotted lines, the graph of tan x is undefined, and the graph of tan x repeats every pi radians, which means it repeats every 180 degrees. Now let's look at the transformations. We'll start with y equals sine x plus a. So we're going to use sine x for all of our transformations, but the transformations work the same for cos x and tan x as well. So y equals sine x plus a is a translation in the y direction by a units. This means that we're shifting in the y-axis by a units. So as you can see on example number 1, we've defined f of x as sine x, and g of x is f of x plus 1. So we have our f of x here in gray, and then g of x is f of x plus 1. So we've shifted by 1 unit in the y direction, and you can see that our blue graph here, g of x, is above the gray graph by 1 unit. So for example, the starting point of the graph here, we can tell that it's shifted up by 1 unit. This point is also shifted up by 1 unit. So y equals sine x plus a, that's a translation by 1 unit in the y direction. Now let's look at y equals sine x plus a, but this time the a is inside the bracket. So if a transformation is inside the bracket, there's a transformation in the x direction or in the x-axis. And in this case, it's x plus a, so it means it's a translation. And for a translation in the x direction, we'll take the opposite. Since it's plus a, it means we're moving by negative a units. Let's look at an example. Here we're given that f of x is sine x, for x is between negative pi and pi. And then we're given that g of x is f of x plus pi over 2. So you can tell here that we have a translation in the x direction by negative pi over 2 units. So again, we're starting with our gray graph over here, that's f of x. Let's look at this point. This point is now the starting point for the blue graph, as you can see here. And if you calculate the difference between these two x values is negative pi over 2, which is the same number of units that we are translating by. Again, if you come to this point here, you notice that it has shifted by negative pi over 2 units, as well as this point by negative pi over 2 units. So sine x plus a, when the a is inside the brackets, is a translation in the x direction by negative a units. Now let's look at y equals a sine of x. So this a represents a stretch in the y direction by a stretch vector of a. Let's look at an example. So we're given that f of x is sine x, and we're given that g of x is 2 f of x. So we've multiplied f of x by 2. This is a stretch in the y direction by stretch vector 2. Our gray graph is the graph of f of x, our blue graph is g of x. You can see that on the y, this point is 1 unit over here, but on the transformed graph, this point is now at 2 units on the y-axis. So that means we've multiplied f of x by 2. And again, if you do it for this point here, it's now been multiplied by 2. It was -1. -1 times 2 is -2, so it now ends up here. Now let's look at y equals sine a of x. Again, this is inside the brackets, so this means that this is a transformation in the x direction. And since the a is multiplying the x, it means that this is a stretch, so it's a stretch in the x direction. And the stretch vector will be the reciprocal of whatever number you have here. So in this case, we have a. So it means our stretch vector would be 1 over a. If you have 3, your stretch vector is 1 over 3. If you have 1 over 4, your stretch vector is 4. So the stretch vector will be the reciprocal of whatever number is over here. So let's look at an example. We're given that f of x is sine x, and we're given that g of x is f of 2x. The 2 is inside the bracket, and it's multiplying the x. That means our stretch vector is half. So it means we're going to multiply each point by half. So on the original graph, we have this point pi over 2. If you multiply it by half, it becomes pi over 4. And as you can see on the blue graph, it's now at the point pi over 4. We can also do the exact same thing for the point at pi. On the gray graph, pi is over here, but you can see that on the blue graph, pi is now at pi over 2. That's because we've multiplied it by half, which is our stretch vector. So if you have y equals sine of ax and the a is inside the bracket, then that means this is a stretch in the x direction. So those are all the transformations you need to know. Just to recap, we have a translation in the y-axis, which is y equals sine x plus a. We have a translation in the x-axis, which is sine x plus a, but this time the a is inside the bracket. Then we have a stretch in the y direction, which is y equals a sine x. And then finally, we have a stretch in the x direction, which is y equals sine of a of x. Now we can also combine all of these transformations to become one big combined transformation. So that's what we have here. We've got y equals a sine of bx plus c plus d. If you follow this principle over here, all of these transformations, it means that this a over here is a stretch in the y direction. This b over here is a stretch in the x direction. This c over here is a translation in the x direction, and this d over here is a translation in the y direction. So in past papers, usually your transformations are given as combined transformations. So you should master the basic transformations first. You should be able to apply the principles for the basic transformations into a combined transformation. So now let's look at an example. We're given that f of x is sine of x, and we're given that g of x is 3f of 2x minus pi over 4. So let's start with this 3 over here. This 3, we said, represents a stretch in the y direction. So we've got a stretch in the y direction by a stretch vector of 3. Then this 2 over here represents a stretch in the x-axis by, remember we said for the x we're going to take the reciprocal, so the reciprocal of 2 is 1 over 2. And then this negative pi over 4, that's a translation in the x-axis by pi over 4 units. Remember that we say that we take the opposite sign again for the x. So if it's negative pi over 4, it means we've shifted by positive pi over 4 units. And finally, this one is a translation, and the y-axis by 1 unit. Okay. So if you understand these transformations, you should then be able to sketch the graph of g of x. So that's all for today's video. If you learned something from it, please subscribe for more videos like this. Thank you for watching.